Hello folks, welcome back. So let's go ahead and do the second part of the same unit associated with Kirchhoff's laws and application of Kirchhoff's laws to simple circuits. And this is very important because this is the business end of the previous unit. Namely, the previous unit taught us a lot of things at a conceptual level. Now we're actually going to go ahead and get very practical, get our hands dirty with some problem solving. So let's go ahead and focus on that. What I'd like to do is begin with the 7 tips that we set up at the end of the previous unit, which is tip number 1, and we'll go through it really fast. Tip number 1, replace any combination of resistors in series and parallel by its equivalent resistance. Tip number 2, don't be afraid. Go ahead, draw some direction for the current. Usually on a test or an exam, we'll probably have that direction for the current that we want you to pursue drawn for you, in which case just follow that direction. But be not afraid, because um, even if there's no such thing as a right direction. Whatever direction you choose, as long as you apply the rules properly, it will all work out correctly in the end. Tip number 3, when traversing a resistor in the direction of current flow, you will have a negative voltage drop that you add into your loop law. So if you're traversing the resistor from A to B in panel A, you will actually have a voltage drop of minus IR. On the other hand, if you're traversing a resistor in panel B, or in figure B, from A to B, from point little a to point little b, then you're traversing it opposite to the direction of current flow, and for that you have to put a voltage rise of IR. Batteries work the same way. The traditional direction of traversing a battery is from the negative plate to the positive plate. So in figure C, if you're going from little a to little b, then you're going from the negative plate to the positive plate, which is why you have a voltage rise. In figure D, you're going from A to B again, but this time you'll be going from the positive plate to the negative plate, so you have a voltage drop given by the EMF of the battery. Um, Tip number 5 says, apply the junction rule to each junction and go ahead and simplify your problem as much as you humanly can, because you essentially want to do the problem with the least number of independent variables, namely currents, in each loop. Tip number 6 says, apply the loop rule to all the independent loops. Applying it to all the independent loops will basically dramatically simplify your life. It will mean that you'll have the smallest possible linear system that you'll have to invert in order to find the currents in all the loops. And tip number 7 says, go ahead and set the potential to be 0 at any point and go around each of the loops that you're considering and and make sure that for whatever direction of current you eventually got, you have 0 voltage drop as you go around that loop. So it might actually help to draw one figure with the given directions of currents that are given on the test, draw another figure with the exact directions of the current shown according to what you got as an output from the solution of your linear system in tip number 6. That might be a good idea. To do a little extra work but be absolutely extra sure. So with that, let's go ahead and dive in. Now there's a whole bunch of additional ideas and rules that are given to you, or additional suggestions given to you. One of the things that I really like is to make the observation that a capacitor that is uncharged and instantaneously thrown into a circuit basically behaves like a closed circuit. But a capacitor that has been allowed to stay in a circuit for a very long time essentially goes ahead and reaches a steady state where it behaves like an open circuit. So that's actually this puppy out here. We'll actually see in time when we get to the next unit why this rule is in fact particularly meaningful. But all the other tips on this page basically help you to simplify the problem as much as possible. And essentially, I know of no particular way to build up good intuition in this regard, except practice and more practice and more practice. And the more practice that you get, the better your intuition will become. So you can actually go ahead and read these ideas about conceptualizing and categorizing but a few good examples that you do with full engagement will actually help you even further. So you can analyze the solution and then actually solve the simultaneous equations and see if you're getting a good reasonable answer and so on and so forth. So go ahead and read all these strategies that are being shown to you. But essentially, you have to develop an intuition, and if your intuition is sharpened, everything will. So let's go ahead and look at this next problem. It's actually a work problem, so everything is given to you in the notes that you're in the or in the PDF that you're going to be downloading from the website. But let's go ahead and solve this problem as given. So I have everything blanked out here because we're going to solve this problem together in real time. So let's go ahead and solve this problem out here. And we're going to go ahead and say that let's apply the junction rule at point B. Notice at point B that the current I is coming into the junction. So we're focusing on point B out here. The current I is coming into the junction. So we say that I is equal to the currents I1 plus I2, which are actually going out of the junction. So we have I is equal to I1 plus I2. So that takes us through the junction rule, and that's a good thing because it basically is telling us that if we ever see an I in one of our equations, we can legitimately erase that off and replace it with I1 plus I2. The benefit of that is that we will actually reduce the number of independent variables that we will have to use in solving the problem. So with that, let's go ahead and focus on the second suggestion that we've been given. So the first suggestion is apply a junction rule judiciously to all the junctions in your circuit. The second rule, the second suggestion given to us, so it's a guided problem solving strategy where we are given suggestions already to begin with and we have to just follow it. So the second strategy is telling us that go ahead and consider the loop A, B, C, D, E, F, A. In other words, go around the outermost loop in the circuit, going kind of like this all the way around, and ask yourself what voltage changes you have as you traverse this loop. So let's go ahead and start at F and go through the battery. So we have a voltage change of plus 12 volts because we're going through this battery in the conventional direction. So we're going from F to A. Then we can zing from A to B and B to C with no further voltage change. But then from C, we're going to go downward in this leg of the circuit. Okay, and we're going to go ahead and go through the resistor in the direction of current flow, which means that we have minus 2 ohm resistor with a current of I2 going through it, and this resistor, this 2 ohm resistor is being traversed in the direction of current flow, which means that its voltage is dropped. Okay, then we come to the 5-volt battery on the right, and we're going to go ahead and traverse this 5-volt battery in the direction that is opposite to the direction of current flow. In other words, we're going to traverse this battery from up to down, which is opposite to the conventional direction in which we're going to traverse the battery. And so we will actually go ahead and say that we have minus 5 volts as we traverse the 5-volt battery from top to bottom. In other words, we're going from the positive plate of the battery to the negative plate of the battery, and therefore the potential of the battery or the voltage of the battery acts negatively. And then we find ourselves at the point D, and we can go from D to E without any voltage change. And then to kind of come back to the original location F, we're going to have to go from E to F. Notice that as we go through E to F, we're going to have to go through that left lower 3 ohm resistor in the direction of the current I. So we'll actually go ahead and say that we have minus 3 ohms times I, But that's where it becomes interesting, because we realize that wherever we have I, we can actually replace it with I1 plus I2. So why not simplify our life and our equations by going ahead and erasing off I, and in place of I, we just put I1 plus I2. Okay? And that brings us to the original starting point, which was F, and so we say that this is equal to 0. Okay? Now, this equation has to be simplified, so we actually see that we have 12 volts minus 5 volts, which is 7 volts. So we put 7. Then we have I1 and I2 in the circuit. Notice that in front of I2 we just have minus 3 ohms, so we put minus 3 I1. And then in front of I2 we have minus 2 ohms and minus 3 ohms. So that gives us a total of minus 5 ohms. So we put minus 5 times I2, and that is equal to 0. Okay? So we have one equation which basically can be cleaned up now, and we can clean it up and write it as 3I1 plus 5I2 is equal to 7. So this equation and this equation are basically the same thing. Now we're going to follow this third suggestion that is given to us, which is this one, which says that apply the loop rule to the other independent loop, and you have a choice. You can actually go ahead and choose B, C, D, E, B, but that's not the choice that is being suggested to us. The choice that is being suggested to us is A, B, E, F, A. So let me go ahead and take my eraser and erase out the first loop that we drew, clean up everything, and go ahead and now prepare ourselves for applying the loop rule to A, B, E, F, A. Namely, we're going to go around in this loop out here. Okay? So again, we start at F and we go through the battery in a clockwise direction. So we're going through the battery from F to A, which is the conventional direction in which we would traverse a battery, namely from its negative plate to the positive plate. And therefore, we have a voltage rise of 12 volts. Okay? That brings us to the point A. And then we go from A to B without any change in voltage. And then we're required to go from B to E. So we're going from B to E, and we realize that the current I1 is pointed downward in the 4 ohm resistor that we're just about to traverse. And so we have a voltage drop of minus 4 ohms times I1. And that brings us to the point E, and from point E, we're actually going to go back to the point F. From point E to the point F, we're going to traverse the 3 ohm resistor, and again, happily enough, we're going to traverse it in the direction of current flow, namely in the direction of the current I. So we have a voltage drop given by minus 3 ohms times I. And again, we see an opportunity for simplification. So instead of having I out there, we were going to replace it with I1 plus I2. So we quickly erase off I, and we go ahead and put I1 plus I2. Okay, this is equal to 0. Now again, we can go ahead and simplify this equation, and we would like to do our simplifications as quickly as possible. So we see that we have 12 volts. There's no other voltage in this equation. So let me kind of clean up a little bit. Okay, and we have 12 volts. And then if I consider I1, I'm actually going to have minus 4 I1 minus 3 I1 building up to minus 7 I1. Okay? And then we have minus 3i2. So we have minus 3i2 is equal to 0, which actually tells me that I can rewrite this as 7i1 plus 3i2 is equal to 12. So 7i1 plus 3i2 is equal to 12. This is one of the equations that we're going to work off of. And the other equation that we're going to work off of is 3i1 plus 5i2 is equal to 7. So those are the cleaned up versions that we get from applying Kirchhoff loop rule to the two loops that are given by A, B, C, D, E, F, A, and the loop given by A, B, E, F, A. That's the suggestion made in this problem. Now we actually realize that we have to get rid of I1 or I2. The strategy for getting rid of any one of them, so let's go ahead and zoom in on I2 and say that we would like to get rid of I2. How do we get rid of I2? The answer is that we go ahead and say that we will go ahead and take the first equation, which is 3i1 plus 5i2 is equal to 7, and realize that if we multiply by 3 through the overall equation, we actually get 9i1 plus 15i2 is actually equal to 3 times 7, which is 21. We can now take the second equation that we marked out and realize that if we multiply this one through by 5, then we get 3 times 5, which is 15 of I2. And that actually makes it very amenable for cancellation. So we'll go ahead and multiply the second equation that we marked out with 5. So 7 times 5 is 35. So we have 35I1 plus 15I2. And that is actually equal to 12 times 5, which is equal to 60. Now, if I go ahead and subtract the first equation from the second equation, in other words, I'm basically doing a little switch. So, okay, I'm doing a little switcheroo. I'm going ahead and writing the second equation first. I have 35I1 plus 15I2 is equal to 60. And then I have 9I1 plus 15I2 is equal to 21. I go ahead and subtract the first of these equations from the lower equation from the upper equation. So I get 15I2 minus 15I2, which means that I get rid of I2. I have 35I1 minus 9I1, which is actually equal to 26I1. So I have 26I1 is equal to 60 minus 21, which is actually equal to 39. So I1 is just 39 divided by 26, which means that I can go ahead and obtain 26 I1 is equal to 39. So I1 is actually equal to 26 over 39. I'm sorry, 39 over 26, which is actually equal to 1.5 amperes. Okay, having obtained I1, I can go ahead and stick I1 into any one of these equations. So I can start with 7 minus 3 times 1.5 minus 5I2 is equal to 0, and I can clean this up. So I get, this gives me I2 is equal to 0.5 amperes. And now that we have I1 and I2, we can actually go ahead and find I, which is just the sum of I1 and I2. So I get I is equal to I1 I'm sorry, let me clean up a little bit. I get the result that oops, bad idea. Okay, so the page flipped over because I made a small mistake. Let me go ahead and continue with this. So we actually get I is equal to I1 plus I2, which means that we found I1 to be 1.5 amperes and I2 to be 0.5 amperes. So therefore I is equal to 1.5 plus 0.5, which is equal to 2 amperes. So that was a nice save. Didn't matter that the page flipped over. But this next part is actually going to go ahead and put us through something very useful and very helpful. So what we're going to get put through is the understanding that not just are we required to go ahead and find the currents and voltages in the circuit, but it is also beneficial for us to be able to find the power usage in each of these batteries, or the power supplied by each of these batteries, or the power drained by each of these batteries, and also the power drained by each of the resistors. Now notice that a battery can actually supply power if the true current is flowing through it in the traditional direction of current flow, namely from the negative plate to the positive plate. However, the battery can also drain power if current is flowing from the positive plate to the negative plate. So when it comes to batteries, you have to be acutely aware that a battery could supply power to a circuit, which we would call the positive amount of power that is conventionally supplied by a battery to a circuit. But the battery can also drain power from a circuit if the current is flowing from its positive plate to the negative plate. Now notice that happily enough, we got I1, I2, and I all being positive, which means that the directions of current flow that we've identified in this picture are in fact the directions that we should be having in the problem. And that's a very good thing. So we actually realize that through the 12-volt battery out here, we have current I flowing in this direction, and I is actually equal to 2 amperes. So the power through a battery is just equal to its EMF, which in this case is 12 volts, times the current flowing through it, which is 2 amperes. And we see that the 12-volt battery is actually going to be supplying power to the circuit, and it supplies a total of 24 watts of power to the circuit. Now let's focus on the 5-volt battery. We have a current I2 going from top to bottom in this situation. So I2 is equal to, let me see if I can go ahead and erase I2 and write it a little better. So we have I2 is equal to 0.5 amperes going downwards. Now notice that if it's going downwards, it's going from the positive plate to the negative plate of the battery, which means that it's going in the opposite direction of the conventional direction where a battery actually tries to supply energy to the circuit. So therefore, the power supplied by the battery is in fact negative, which means that the battery, if it were rechargeable, is actually draining 5 volts times 0.5 amps of power from the circuit. Namely, the battery is actually draining 2.5 watts from the circuit. So we'd write it as negative 2.5 just to indicate that this battery, the 12-volt battery, is supplying power, whereas the 5-volt battery is actually draining power. So now that we have that concept clear, we realize that the total power supplied by all possible batteries in the circuit is just equal to 12 watts minus 2.5 watts, which is equal to 21.5 watts. Now when it comes to capacitors, we have a completely different story. Why do we have a completely different story? The answer is that as long as a non-zero current is going through a capacitor always drains energy from a circuit. Why does it drain energy from a circuit? The answer is very simple. the power drained by a capacitor is always equal to its resistance times the current squared. So it matters not whether the current is positive or negative. The point is that the capacitor, I'm sorry, not capacitor, but resistor. It matters not whether the resistor has positive current flow or negative current flow. The power drained by the resistor is always equal to Ri squared. And so regardless of whether I comes out to be positive or negative in that circuit analysis, the point is that a resistor always drains power from a circuit. This is not unreasonable, because you realize that as long as there's any current flow going through a resistor, that current is actually produced by electrons that are banging up against the atoms that make up the resistor, and therefore draining the electrical energy in the circuit, and basically turning it into thermal energy or heat energy, which is radiated away by the resistor. So we realize now that across this 4 ohm resistor out here, it has a current of 1.5 amperes going through it. So we just do 4 ohms times 1.5 squared. And that, if you just tap away in your calculator, turns out to be 9 watts of power. And this is always being drained by the 4 ohm resistor. So we indicate the power drained by the 4 ohm resistor by writing this nice little subscript of 4 ohms next to the power. Now let us focus on the 2 ohm resistor out here. Again, we have I2 going through it, which is a current of 0.5 amperes. So we say that the power drained by the 2 ohm resistor is just equal to 2 ohms times 0.5 amperes squared. And if we tap away at a calculator, we'll find that that is equal to 0.5 watts. Now let us focus on the 3 ohm resistor out here. We realize that it has 2 amps of current flowing through it, and therefore we will say that the total power drained by the 3 ohm resistor is just given by P with a subscript of 3 ohms, and that's equal to 3 ohms times 2 amps squared, which gives us a total power drain of 12 watts. Notice that we can add these up. So we can add up 9 watts to 0.5 watts to 12 watts to get a total of 21.5 watts. Notice, happily enough, that the power dissipated by all the resistors is actually equal to the total power supplied by the batteries. Now, the batteries could have supplied power or drained power from the circuit, but we realize that as long as we do the arithmetic correctly, the total power supplied by all the batteries in the circuit must be equal to the total power drained by all the resistors in that circuit. So this tells us that we've obtained a nice little solution to the problem, and now we're ready to move onwards. So happily, we've gone ahead and solved one problem very thoroughly. Now let's go ahead and focus on our next problem. So in the next problem also, the directions of current flow have been worked out for us, and we don't have to think much. Okay? So let's go ahead and focus on this picture out here, which is basically telling us that, or which is basically providing some hints to us and telling us how the solution will go. So we realize that across the 8-volt battery, the current I1 is going upwards, or at least that is the direction we've been asked to accept for now. Across the 4-volt battery, which connects E to B, we're again told that the current I2 is going up. And across the 6 ohm resistor on the right, we're told that the current I3 is going down. So we can actually go ahead and say that applying the junction rule at the junction B out here, we have a situation where I1 plus I2, which are both coming into the junction, is equal to I3, which is flowing out of the junction. So that is just the application of the junction rule. And so we're going to basically set up a convention which says that wherever we have I3, we're actually going to replace I3 by I1 plus I2 and simplify our lives. Now the next question asked of us is, how many independent currents do we have? The answer is that I3 is not independent because it can be written entirely in terms of I1 and I2. Therefore, by application of the junction rule at junction B, we actually realize that we have only two independent currents that we could use. Now, you can actually go ahead and make your life more complicated by considering all the currents, but why would you do that? You just want to solve the problem in the simplest number of variables that there are, right? So let's go ahead and say that the number of independent currents is 2. Question now is, how many independent loops do we have? And we've gone ahead and practiced this several times now. So we realize that out of the 3 possible loops that we can have in this circuit, only 2 of them are independent. And so we write our answer to that question as also being 2. Then the question asked of us is, can you apply the loop rule to the loop A, B, C, D, E, F, A? Okay, so that's the loop where we're starting here and going around the entire circuit like so. Of course, we'll erase that off and when we apply it to the next loop. So let's go ahead and nevertheless write the sum of all the voltage changes. So we realize that if we go from F to A, we're having a voltage rise of 8 volts. So we write 8 volts rise. Then we go through the 1 ohm resistor on the left top, and there's a current of I1 going through it. So we'll have a voltage drop of minus 1 ohm times I1. Then we go through the 4-volt battery that is on the top leg of this circuit in the segment A to B. So we have a voltage rise of plus 4 volts. Then we go through the 2 ohm resistor at the top, and we're traversing it in the conventional direction of current flow, namely in the direction of I1. So we have a voltage drop of minus 2 ohms times I1. And that brings us to the point B. We can go from point B to point C with no further voltage change. And then we go through the 6 ohm resistor downwards on the right. And so we have minus 6 ohms times I3. So we can go ahead and in principle write I3, but we have always our simple policy that if we can simplify a problem ASAP, we actually do that. And so in place of I3, we will actually write I1 plus I2. And this in turn is equal to 0. So we come up with the realization that we have 8 volts plus 4 volts, which is actually 12 volts. Okay? We can have minus 1 I1, we have minus 2 I1, and then we have minus 6 I1. So minus 1, minus 2, which is minus 3, minus 6 gives us minus 9 I1. So we have minus 9 I1. And then we consider I2, and the only thing that we have is minus 6 I2. So we have minus 6 I2. This is equal to 0. And it behooves us to actually write it down in a nice cleaned up fashion. So we will actually go ahead and divide everything by 3. So we actually get 3I1 plus 2I2 is actually equal to 4. So this is one of our important equations that we're going to work off of. Let's now go ahead and erase this loop that we have considered and draw, as it were, the next loop that we've been asked to consider, which is BCDEB. So we're going to go ahead and consider this long skinny loop and traverse it like this. Okay? So for this loop, let's go ahead and realize that we have, through the 6 ohm resistor, we are traversing it in the traditional direction. So let's go ahead and start at C and go down to D. So we have minus 6 ohms times I3. Okay? And we follow our principle, which is that we immediately erase off I3, and in place of it we put I1 plus I2. Okay? Then we come down to the point D. From point D to point E, we can go without any voltage change, but then we're traversing the battery, the 4-volt battery, as we go from E to B, and as we go from as we go from the point E to the point B, we're traversing the battery in the conventional direction, namely from its negative plate to its positive plate. So we have plus 4 volts. Okay? And then we're traversing the 2-ohm resistor out here in its traditional direction. So we have minus 2 ohms times I2 as being a further voltage drop across the 2-ohm resistor. And that is equal to 0. And that actually allows us to go ahead and write this as another equation. So this equation is completely equivalent to the equation which says that we have 4 volts, so 4, then we have minus 6I1, and so we have minus 6I1, and then I have minus 6I2 minus 2I2, which is minus 8I2. This is equal to 0. Now notice that I'm noticing a factor of 2, which I can simplify with. So I would actually obtain 3I1 plus 4I2 is equal to 4 divided by 2, which is 2. And so I can actually go ahead and why not simplify this equation even one step further and write it in its absolute simplest form. So we'll actually go ahead and write it as 3I1 plus 4I2 is equal to 2. So we realize that this is another one of our important equations. So now we have two important equations. 3I1 plus 2I2 is equal to 4. And we have another important equation which says that we have 3I1 plus 4I2 is equal to 2. Now what we're going to do is we're going to go ahead and line these two equations up, and we're going to do our subtraction of equations. Notice happily enough that we have 3I1 and 3I1 in both these equations, so we don't have to work too hard, and that's a good thing. So we have 3I1 plus 2I2, I'm sorry, is equal to 4. That's what we get from the first equation that we marked up. And from the second equation that we marked up, we have 3I1. Let me write I1 properly. Plus 4I2 is equal to 2. And so if I go ahead and subtract, I get the result that, so if I subtract the lower equation from the upper equation, I get the result that I have minus 2I2 is equal to 2, or equivalently, I can go ahead and say that I2 is equal to minus 1. Okay? Now I can go ahead and put that into one of the equations. So I have 3I1 plus 2 times minus 1 for I2 is equal to 4. Okay? And that tells me that 3I1 minus 2 is equal to 4, or 3I1 is equal to 6, or I1 is equal to 2 amperes. So we got I2 is equal to minus 1 ampere, and I1 is equal to 2 amperes. And this tells me that I3 is equal to I1 plus I2. That's just this expression out here. So I get I3 is equal to I1 plus I2, which is 2 minus 1, which is 1 ampere. Okay? So now I realize that I have solved the problem at least to the point where I have obtained all the currents in this system. Okay, so the currents are in the bag. Notice that we have to actually be a little adaptable. So I1 came out positive, which means that we chose the current in the left leg of the circuit going upward as correctly drawn. However, notice that I2 came out negative, which means that in the middle leg of the circuit, we probably should have drawn I2 coming downwards. And I3 came out positive, which means that the direction of I3 that we originally chose is in fact the good direction, which is the direction which says that I3 is indeed flowing downwards. So with this understanding, let's go ahead and focus on parts B and C of this problem, which essentially deal with the amount of power flowing in the batteries and the amount of power flowing in all the resistors of this problem. So that's actually what we're going to focus on in the next transparency. And notice that we've brought over our values or our evaluation of I1, I2, and I3. And I2 is in fact negative, so we can actually go ahead and flip I2, make it go downwards, and say I2 now with the flipped direction is 1 ampere. I1 is equal to 2 amperes, so we'll write I1 is equal to 2 amperes out here, and I3 is equal to 1 ampere. Okay, so now part B of the problem essentially tells us to obtain the power supplied by each battery, and part C tells us to obtain the power dissipated by each resistor. Now let's go ahead and do our job with respect to part B. Part B says that we have to find the power supplied by the battery, which is the 8-volt battery. So we'll write P 8 volts. And that is actually having current I1 flow through the conventional direction in the battery, that is on the left leg. And so we have a current of 2 amperes flowing through in the conventional direction through the 8-volt battery. And so we can write this power as 8 volts times 2 amperes, which is equal to 16 watts. Okay, so that gives us the power supplied by the 8-volt battery, and it's actually giving that amount of power to the circuit. Now let's focus on the 4-volt battery at the top. So we'll write this as power supplied by the 4-volt battery at the top. And that battery is also carrying a current I1, which is now flowing in this direction through the 4-volt battery. And we can therefore say that that's equal to a power supplied by the 4-volt battery on the top, and that's equal to just 4 volts times 2 amperes, which is equal to 8 watts. Now let us focus on the 4-volt battery that is in the center leg between B and E. So this is actually the 4-volt battery, and we'll say that that's the battery at the bottom just to distinguish it from the 4-volt battery on the top. So this is the 4-volt battery on the top, this is the 4-volt battery on the bottom. Okay, so we'll say that the power supplied by the 4-volt battery on the bottom, and that power is actually equal to 4 volts. But in this case, this current is actually going from its positive plate to the negative plate. So it has to be considered negatively. So we obtain minus 1 amperes. And that tells us that we have minus 4 watts of power from the 4-volt battery at the bottom. Namely, this puppy out here, this guy that I'm making dark, is actually not doing its job of supplying any power to the battery. This is actually hogging or draining off power from the other two batteries. So we get the total power supplied by all batteries The power supplied by all batteries is equal to 16 watts from the 8-volt battery on the left plus 8 watts from the battery 4-volt battery on the top minus 4 watts from the battery at the bottom. And so that's equal to 16 plus 8 minus 4, that's 16 plus 4, which is equal to 20 watts. So we have a total of 20 watts of power supplied by the batteries. Okay? Now, the next part of the problem asks us to find the power dissipated by each of the 4 resistors in this circuit. So to help that along, let me go ahead and clean up the stuff that we marked out for the batteries. Okay? And we will actually just keep or retain the current flow in the resistors. So we have the power supplied by the 1 ohm resistor at the top. So we say that the power supplied by the 1 ohm resistor is actually equal to 1 ohm times the current of 2 amperes which is flowing through it. So we have times 2 amperes squared. Remember that the power supplied by the power dissipated in a resistor is actually equal to its resistance times the current squared. So if I've said supplied by the resistor, please forget that. It's always the power dissipated by a resistor. A resistor has no option but to dissipate power. So the 1 ohm resistor that we're considering in the top leg of the circuit between A and B is actually dissipating 4 watts of power. Now let's consider the 2 ohm resistor at the top. That's this one that I'm marking out. So the power dissipated by the 2 ohm resistor at top is actually equal to 2 ohms times the same current of 2 amperes that is flowing through it. So we do 2 amperes squared. And that answer turns out to be 8 watts. So again, the resistor in the top is actually dissipating 8 watts of power. Then we go ahead and focus on the 6 ohm resistor on the right of this circuit. So we say that the power dissipated by the 6 ohm resistor, and that resistor is unique, so we don't have to be specific about anything, is equal to its resistance, which is 6 ohms, times the current flowing through it squared, which is just 1 amp squared. So that's equal to 6 watts of power from that resistor. And the only other resistor that is now present in the circuit is the 2 ohm resistor that I'm marking up right now. Since we've called one of the 2 ohm resistors the top resistor, we'll call this resistor that we're considering right now to be the bottom resistor. So we have P 2 ohms from the bottom resistor, and that's equal to 2 ohms. Let me go ahead and write my ohms a little nicer. So I have ohms like this, 2 ohms times the current flowing through that 2 ohm resistor. We could think of it as -1 or 1. It matters not because that is going to be squared, and so the sign will disappear. So we have 2 watts of power dissipated through the 2 ohm resistor at the bottom. If we sum up all the power from all resistors, that's equal to 4 watts from the 1 ohm resistor at the top plus 8 watts from the 2 ohm resistor at the top plus 6 watts from the 6 ohm resistor on the right side plus 2 watts from the 2 ohm resistor at the bottom, and that gives us a total of 20 watts of power dissipated in the resistors. Notice, happily enough, and exactly as expected, that we have 20 watts of power total supplied by the batteries, and that does indeed and must indeed match up with the power drained by all the resistors. So this gives us another very good problem with a very good feeling about that problem. And that brings us to the last problem that is there in this unit. I will essentially not go ahead and solve this problem for you. Rather, I will leave it as a problem that we will solve together in class. Okay? And hopefully we solve this problem together in class and we develop a better appreciation by working through the problem together. And of course, you guys are welcome to go ahead and transcribe this problem to your book and solve it even before you come to class so that you get a better appreciation of the problem. Again, the problem will take us through the process of solving for all the currents and then going ahead and solving for the power supplied or dissipated, power given or drained by any battery configuration, and also the power dissipated across each of the resistors. And that will be a very good exercise that will teach us or give us even more practice. We've already done 2 practice problems. We'll do a 3rd practice problem. You'll probably get a practice problem in tutorial and probably 1 or 2 at least in your homework. So that gives you tons of practice problems with respect to Kirchhoff's laws. And hopefully, with all that practice going in, you guys are going to be super prepared for whenever you face up to a big Kirchhoff law problem on a test or an exam. So with that, I will thank you all very much for your attention. Hope you get rewarded for all the attention that you've given and all the time that you've given. And I do intend to reward you all, of course. So thanks a lot for your attention and see you all later. Thanks. Bye-bye.